slideshow.
What's the problem?
Well, it's just not.
What I want to do is I want to see your laser. It's right from that presenter, you can probably switch the screens.
Yeah. So if I grab and slide over, I go over here. Wait, you can see it's my mouse. We're just trying to get it real quick.
If it's not working, I'm just closing it.
Yeah.
It's something else.
So I'm gonna try my computer.
See, this is why I don't like PowerPoint. It's all about Keynote.
So Keynote's better.
Oh yeah.
Well, then why don't I just present it in PowerPoint Keynote?
Because you know what it looks like. Is that HD?
Yeah, no, that's VGA.
Oh, so you already have the connector. Good. Try it.
I'm just gonna try my computer out.
So we are on air officially.
So tell me how that webcam thing works. If there's a webcam, you can use it to broadcast?
Yeah. Have you ever heard of so you know Google Hangouts? Like we called each other on that one time. You can actually do what's called a Google Hangouts live or Google Hangouts on air and live broadcast your Hangout. So everybody that was on our list has an invite to this Hangout. And they can just join.
Cool.
Yeah, it's pretty awesome. And it saves the video automatically for you. Works out pretty well.
Turn your Wi-Fi on too. Close your email.
Do you think?
Oh, yeah, because it can, well,
I get you reminders.
it can start to mess up stuff.
Jim Larson. I don't know why I'll okay. I think we got everything worked out.
Just, needs one to run out from here. It's on here.
I think everything probably should be back. Let's see. I had it laid up into my bag.
So I have to be too prepared.
Yeah, that's what it is.
You just need a power cord?
No. We're all good.
Ooh.
Wow.
So this works. That's Kian. I'm gonna move over here.
Good.
Welcome, thank you for making the trip.
Oh,
Remind me of your name.
I'm Shadow Cyrus.
Cyrus. You have a different name? You go by Cyrus, but
Yeah, I've got my two different names. Shadows is good.
Shadows.
Shadows. shadows, shadows, shadows. It's sharp, it's kinky. Rose means name. Yeah, Rose means day. He's the king of the day, which means sun, the sun.
Oh, cool.
Yeah, so I mean, it's like.
So yeah, it's perfect for a thing like daylighting.
Daylighting
So
taxes.
your name is Showers and you
King of the sun.
But you switched from showers to sirens.
No, actually, it's not because that's a long story. My father's name is Behruz, and my father wanted to showers because it has a long like close with it. And my mom wanted Cyrus. I ended up having my father won't.
So it worked.
Yeah.
Is it looking fun? Try it.
Yeah, I'm gonna open this last one. And it probably don't work. I'm in Kenya. I think all of it looks okay. Which will probably,
Doing
balcony TV. Slides on it. Pretty cool. Technical difficult.
No idea what you're doing.
about the disease of the performer transition. Film
Okay, where's my subject? Sadly.
He's on to it.
I'm his back, he's
Okay,
Where's he gonna go?
next one.
I'm just gonna go.
We can pull up those lines too.
Hey, it works on this.
I got those grass out there.
Okay.
Okay, well, what's the next slide button?
It's just next.
Maybe a visual clue, if like, will you be standing in the back? So,
picture.
so when I say, okay to you, you could give them a clue.
I can call him.
You could call them, yeah. Okay.
Easy peasy. Wonder if we can go to.
Talks about beauty and artistry. It's engineering, true. Trying to remember, see, there's only next arrow, calls that becomes in. So that just popped up. I'm trying to remember what happened to these buttons.
Oh, we just saw, oh, I love it. It's a bonus.
Oh, that is weird.
Do you want to back shape controls?
Hey, Ryan.
No, I've got that. Cool. Something that he's going to.
There's two.
So I've got the live broadcast on my phone too.
So what do you think about talking about things like the Fitbit? So it's on already. Hello?
I think it's a little delayed. How's it going? Good. Let me go. Good to meet you guys.
Yeah, he was here for,
That's me. Yeah, that's me. We're live broadcasting.
that's why. This was a YouTube channel, right?
It's on our YouTube channel. Yeah. Yeah. It'll all be saved after the presentation. everything's over, so you can go back and watch it.
Yeah, I'm home.
Yeah.
It's going to be here.
Yeah, correct, yeah, exactly.
Do you guys get settled in?
We'll start shortly.
All right.
So it seems to work.
Oh, you mean this thing?
Okay.
So, Shawu, is that right, Shawu?
Yes, yes.
What is your daily,
Actually, I just finished the transition phase from 3 to 3. And I just helping a friend. And he's he's kind of freelancing. He's not involved in charity design. And I'm trying to just helping my friend. Business starting a business called Scan. Yes.
Oh, yeah. That's what I emailed you about, because I have some software that takes in point data.
Yeah,
So if he can scan stuff, we can make it into 3D.
for the building sector.
Yeah.
There's a big company that used to do it, but my friend is which is making my job very difficult. He's interested in oil piping situation, oil industry.
Yeah. And it's being,
I
it's
don't
coming
have
to
that
some
enough
different
knowledge
fields.
in piping oil industry.
That's nice.
What's nice is,
Yeah, especially once you know Revit, because you transfer to I know Revit architecture. Revit MEP mostly.
so, that's what you're doing, now. What's your plan? To start this company and then start your own company?
No, actually, I just came here. I was looking for getting being an electrician. Or also an engineer. Either I prefer to get in architecture, which is
There is a TE for
I like that.
the thing. No, I'm taking.
Honestly, you probably just watched
But I didn't know there was one of the things.
Robert PC, the artist is
RPE for architecture.
Yeah.
Sorry.
He's studying for the PE.
No, I'm aiming.
Oh,
I
okay.
haven't studied.
He wants to get his PE in architectural engineering.
Oh, okay, yeah, but
Yeah,
Robert?
there's a.
I think that was Robert.
Yeah, he grabbed the microphone.
Architectural engineer.
Oh,
the, you see it now.
Graduating soon.
no, there. I mean, I'm
I'm Tanteri.
Yes.
So how can you,
I got my master's.
oh, because it's European architecture, you qualify for
You know, I gave to that. I studied.
Oh, so you studied architecture, you got to engineering.
That was a big. Yeah, and then,
You were from about
no, my friend is going to start that leader.
your friend is starting.
Yeah, and he asked me to help him since I was free.
Could look down on roofs.
Hello.
Exactly how it's gonna work, but the one you're working on, you have like, you know, it's like the school campus. You just like, yeah, you just set different points to find the corners that you can see. And then each campus based on the other corners and you all this stuff, but it's kind of smart. Yes, but I'm honestly, that's a question.
And it's still people looking for students for red.
Yeah, that's a different thing.
Not this guy.
You know,
We're all set.
We have been digging more and more into fireplace makeup. And it is, I can tell you something, by telling you, we have asked, so Eric went to the ashtray conference.
trying to exploit the reflection in daylight factor. Really?
Something, yeah.
We recognize it now. Standards.
It's just,
And they also,
I finished this one,
I want, that's what I know, that's like.
but this one haven't.
It's
started.
He's got, he decided, you might take that from us.
So the philosophy part is
He
interesting.
decided to get.
It's based on
After all, we ended up.
that wasn't very easy for me to read. But I was expecting to better doing better job.
And he was still.
And he was sort of hypocrite. So he was explaining something, but he was not doing it in the same way.
That's well, if you look at it from the side, yeah, you can see like the great all. So we kind of included.
He wasn't really looking for
That, you know, Sky.
but overall, I like that.
We're talking about fire. It's not even. So firefights makeup is definitely like a black mark. Well, we have a good example. But then the other thing is, when we're going outside the air vent, I see it. New ones.
Same order.
You know what I think to do to try to avoid. I think so, actually.
I don't know if he has these lines or not, actually, just bring them along there. I don't like to be very. It's our field tester.
You know,
He does a lot of the.
I know. Well, we did find a lot of language in there. You know,
It's not the same.
probably, yeah. That basically says, the manufacturer, going through fire.
It's a so, yeah.
Well, I'm just thinking. That's the other thing.
I know for their, they have a specific engineering.
When you have those.
Yeah.
In fact, I went from this one, but I was
Zephyr. We found out, oh, Zephyr has their own name.
For 1,500 CFM.
Perfect.
Like, instead of go.
That's kind of that last one.
Right.
Not very big. It's good to on that original job. That is not on the market yet.
I think that would be, I mean, it's new, but it's the state's program.
There was something.
And so I was thinking more,
Well,
more executive, design. So they're being convinced to forward care. He wants to build it, so they're similar ways as Austin can they kind of, I was thinking of. Yeah. As an engineer, if it's me, then absolutely you're liable. And same thing for the entire. Yeah, so that would be specific. But I can double check that. But that's just. I think it's probably kind of in. Someone's still taking it, but it's just.
I saw that.
The architectural.
But anyway, So like for these things.
Before there wasn't a program. So I think as park, you know, sign, they'll stop being
No, I know, because I trust you. You was lived so
Yeah. Yeah. Yes, I know. So, and I have resources to University of Texas, staff, so I know.
I'll send you some information.
Yeah, we're ready. We're live.
Okay, the people that are here, or the people that are coming, thank you very much for coming on. Hey. Where did that come from? So that thing can see me.
You're on.
Just kidding. I'm gonna sit. So, Michael.
Yeah.
I can't see the slides.
No, we'll post the slides afterwards.
Okay. So everyone, just so you know, we're gonna get started now, and this is live streaming on the internet, so just keep that in mind. Hold your outbursts and keep it apolitical. So welcome, thank you guys for coming. I know it's not the easiest thing to do on a Monday at lunchtime. We're all busy, facing a lot of work. I'm Christopher Owen with Positive Energy. I'm here with Matthew Tanteri, who's in the back, and with Jim Larson from Cardinal Glass in the back. Good to meet them. We have a lot to go through, so a few preliminaries, and then we'll jump in. 3 parts, 3 presentations. I'm talking about human factors, thermal comfort, specifically focused on the glazing side of things. Jim is going to jump in from the window manufacturer perspective on the material side, and Matthew is going to be talking about comfort, visual comfort from the fundamentals of that, from both the fundamentals and the materials standpoint. So here's my talk. Here's where we start. So the fundamentals of comfort. The key word there is comfort. It takes a little bit of a definition. Probably recognize a lot of faces. I've heard a lot of this before. But basically, your building is in direct relationship with your human occupants that are in there. It's affecting their experience of it. Who we are, we're in full service building science company. We do a lot of integrated design, mechanical design, testing, and things like this. So here's a little icebreaker. First of all, anyone with like a degree in geology in the room? Okay, good. This will make more sense. So, stone or flame, which is more like this building that we're standing in? Is it more like a stone, solid, sitting there, or is it more like a flame right down here? Anyone? I would remember it's on the internet. So anyone else? So, the answer is very much that it's much more like a flame, because there's energy inputs here, right? There's electricity, there's gas coming in, there's sunlight coming in, a lot of energy coming in. This space that we're in is a dynamic environment, and it's in relationship with the occupants. Here's another example of a dynamic environment. There's a client. And so he's in relation with what? He's in relation with the windows in the space. The windows are constantly mediating heat and light, visual and thermal comfort factors in him. That's what we're going to talk about today. What is something to really keep in mind is that we're adding to the vocabulary now of what it means to design a space. So there's actually a Steve Martin joke. I think he said, that novel was a real breakthrough for me because that was the first one where I started using verbs. And in similar way here, that didn't go over very well. In a similar way here, so we're looking at two spaces, right? So this is space. You guys design spaces. We all are, as a team, responsible for delivering indoor environments like this to the public. So what you can see is that there's windows dominating the space, and we're working with form. But what it means to be formal as an architect is in the process right now. There's a paradigm shift where it's in the process of expanding. When you work with window form, you are working with a thermodynamic form. You're working with a visual comfort form. Right? You're working with an aesthetic form, obviously. That's extremely important. And whenever we're thinking about buildings, there's three intersecting factors that are always happening. Anything in relation to a building could go into one of these. There's aesthetic factors, style, beauty, taste. Right? We don't even have to define those too much. You know it when you see it. You know when something's beautiful. It does change over time, right? I'm not wearing bell bottoms. Rubensian or Rubenesque women are no longer considered to be as beautiful as they once were. Human factors, this gets into direct perception. Aesthetic factors is definitely cognitive, right? You take in data, you process it, you produce a response. There are many factors associated with glazing that are direct human responses that bypass the cognitive centers. And then the last one is definitely a factor that's becoming more in our cultural milieu when it comes to designing buildings. How is it impacting the thermodynamics? How is it impacting the resource use from a planetary, I guess you could say, perspective or societal perspective? So the good news about those aesthetics, direct perception, and resource factors is if you focus on the human factors, meaning everything, the budget, the location, everything, the artistry, then you end up with a building that's very good. Just one example. So a building that has a lot of glazing, or a zoned building that has a lot of glazing, if it's not well thought out and well designed, it's going to have a lot of thermal transients. Right? It's going to have spikes in temperature potential. It's going to have large radiative loads, which is the point of today. And that's a negative from a direct perception standpoint. That doesn't need to be thought, I'm absorbing energy from the window. It's just happening, it's direct. So these human factors, if you can focus on those, good buildings will follow. So we're talking about beauty, satisfaction. Engineers can't handle words like beauty and satisfaction very well, right? So we try to define it. And so instead of saying a beautiful building, we say a high quality indoor environment. We split that up into constituent factors, which when it comes to glazing, it's going to be thermal comfort and it's going to be light. Those are the big ones. In fact, air quality, I think most of us would know that when a lot of UV energy comes in and hits carpet, especially new carpet, it cooks. It has a lot of chemical reactions that occur, so directly you can have light and heat causing indoor air quality issues early on in the building. Usually decreases over time. Sound, odor, and vibration are also interlocking. When it comes to integrating design, when you're working with the design of the building, you are integrating all those factors. You are making decisions about thermal comfort, about visual comfort, about sound, odor, and vibration when you work with form as kind of classically thought of. So that's comprehensive. Now we're jumping in and we're going to talk about thermal comfort. So thermal comfort, remember, is one parameter of the overall, which we take to be that which is integrated to create satisfaction. So thermal comfort, this is actually an ad for these guys. This is thermal comfort data logging station. It's not a radio antenna or anything like that. It's measuring air temperature, air velocity, humidity in the air. Radiant, it's measuring a full 360-degree radiant temperature profile in that space. And it's called the Foundation of People's Wellbeing. That's actually right from their brochure, that picture. And so there's two things to keep in mind here. One is this, that thermal comfort, again, is not a proxy for your environmental quality. It's just thermal comfort. Right? So visual comfort might be impaired even if thermal is good. And the other thing is that our goal is to make high quality indoor environments for people, for humans. So this is like, the quantitative sensor, those are the qualitative sensors. And we are sensor systems. Right? So this is an example of our sensor systems. There's a lot to say about this. In the interest of time, I spared you. I'm not a biomed, but I've learned a lot about this. But a couple things to note is that these sensors here are for heat and cold. They are directly in our skin. Our central nervous system comes to our skin. Those data go directly into our brain, where it hits the thalamus, the hypothalamus, the pituitary, the thyroid, all those things. And in fact, two of those, so our central nervous system is directly responsible for maintaining comfort in homeostasis. Right? So what it does is, when it experiences, let's say, too much heat, I'm absorbing heat from this piece of glass, the very first thing that's going to happen is signal is going to travel from my skin to my central nervous system, to my hypothalamus, down to my thyroid, and it's going to increase blood flow in my skin. Right? That's the first thing it's going to do, try to dissipate that heat. Right? Later, if that's not working, it's going to start causing me to perspire. Right? In the winter, right? If decreasing blood flow to the skin so that I'm not absorbing so much cold into my blood, it's going to start causing muscle contractions, shivering and goosebumps. But we hope our clients never get to either of those extremes, perspiration or goosebumps, in our spaces. But the point is that it's a direct perception. There's no cognitive. I think I will have this circulation through my skin expand now. It doesn't go through that system. When we build buildings like this, we need to be aware of that fact, that we are radiant systems, right? We circulate blood. We have a pump. We have main lines, ducts, branch ducts coming out to our skin to circulate blood. It's actually in this one too. In here, it's talking about the blood flow. And it's just this line here. It's not showing it on that one, but there are cells that control the circulation of blood out of our skin. So what we have is we have a body in a space. That body in a space is wanting to interact by radiating to the surrounding surface temperatures. That is the main strategy our body uses, is radiant heat exchange. We don't pant like dogs, right? We don't. So we're not using evaporative cooling. We move a little bit of air off of our skin, and that moves some heat away. But fundamentally and basically, the way we maintain comfort is by radiant exchange, right? So we're a radiant system. We would love to interact with the walls of the building. When we have something like this with glass and steel, in this picture, it's actually less the glass and more the steel. If there's sun hitting those beams, even the very end of it, it could be 30 degrees out and the steel could be 130 degrees. Right? So that's radiant exchange. Radiant is our next topic, right? So when you think radiant, you don't really think heat. That's incorrect to think heat. It's much better to think light. Right? So if I try to get rid of, like, let's say my attic is hot, it's shining radiant heat down on my ceiling below. Can I move, and it's light, like it's shining light down on my ceiling below. Can I move air through my attic fast enough to overcome the light shining on the ceiling below? No. So if you need to think, line of sight, speed of light, that's radiant. Don't think heat to start with. There is a source of heat, right? Radiant, you want to think thermonuclear fusion. That big ball of sun, that's a fusion reaction. If it were happening anywhere near us, we would have major radiation control devices associated. We have monstrously thick lead-lined brick walls. It's a very powerful force, and it's powerful even when it comes down into an airport here. It moves people from place to place. So, right, it's radiation from the sun. We all know it. We recognize it as light and heat. That little band in the middle, visible light, I think you're familiar with this all. Let's jump into it when we're direction. This is the sun, 93 million miles to the Earth. The space in between us is not hot. It's radiant energy. Once it gets to our atmosphere, some reflects, some bounces back off the Earth, right? So that it heats up the Earth, it bounces back off the atmosphere. This is the greenhouse effect, which, by the way, once the heat is in our building, those windows are opaque to heat. They reflect the heat back in, so you get the greenhouse effect happening in reverse. When we see energy moving from the sun to the planet and back into the atmosphere, these big diagrams, just want to point out, this is radiation. This is not hot air moving around. There's no source of hot air on the planet other than the sun heating the Earth and the water below that air. To a very minor extent, the air has some mass that heats up. There's lots of radiant energy in motion. If we look at intensity in the up-axis and wavelength in the down horizontally, we have two spectrums. We measure the sun, right? We get that ski slope, the big red one, that is extraterrestrial. That's outside the atmosphere. It interacts with the atmosphere, and we get the green one with the bumps. So we're digging into the meat of it now. So you see that, just keep in mind, a big humpy shape and some bumps there on the right. Now we're going to define that a little bit. So you can see we have ultraviolet, visible, and infrared. Keep in mind, visible is a bit of an artificial definition, which is nicely human factored, right? These sense it. That's why we call it visual. It's not fundamentally different from UV or fundamentally different from infrared. So what's important to keep in mind, so here's that hump. So keep in mind, see the green with little humps on the right, tapering down? It got moved into this, it got compressed. So here is the terrestrial spectrum of the sun. This is what we can see. This side over here, we call that ultraviolet. That is skin tanning, skin cancer, cataracts, very high energy radiation, low wavelengths, short wavelengths. So moving to the right of the visible, we have this chunk here. It's an extremely important chunk. It's called shortwave infrared. It's very high energy, high intensity radiation. Any of that, when it comes through into your building, it's going to downshift into this low intensity radiation. That's what's called infrared. Right? So we have high intensity and low intensity. Makes its way through, once it gets into the building, and now, so I am saying, if you think you're hearing this, that light is heat. And when we let light into our building, which we want to do, we are letting heat in. We need to be mindful of it, especially the UV and the shortwave infrared, anything over there in that high intensity. So this diagram, by the way, is out of ASHRAE Handbook of Fundamentals. Obviously, our eyes are going to be dealing with the light side, and our skin is what's going to sense the infrared coming right through. So this is very similar to the diagram that we saw of the sun shining on the Earth. We have sun shining on glazing, it's reflecting back, it's coming through. All this is quantified by the window specs that we work with a lot, and those are just a few of many, many specs. And they're not just numbers, it's not just about code requirement, although that's a fantastic place to start, is meeting code requirements. We're talking about a direct, intimate relationship with the occupants when we talk about this stuff. And so what we've done as an industry is we've said, well, look, if I live in a cold climate, I actually want to allow as much of that high intensity radiation in as I can. That's a high SHGC. We don't live there. We live here, where we really want just the visual. We want to chop off as much of the UV on the left of the visual range and the shortwave infrared, these peaks over here. This is the real danger, right? So the UV and this, that is very high intensity radiation relative to visual. And all of it, once it gets in, it becomes this. It becomes this long wave black body is called radiant heat. So it's good if you're cold. It's not good in the summertime. You want to limit it. Here's an example of Cardinal's curves. And you can see the visual range there up top. And they are chopping out a lot. So here's our good old buddy right here, Louis 366. You can see it's actually taking a little bit out of the light. There's a new one here, 340. It's getting a little better cut, you can see, both in the shortwave and the UV. It also reduces the VT. It also reduces the visual light that's coming through. Okay, so that's the primer on what's coming in, right? We got a sun blasting a lot of energy in. We want to make sure that we keep people comfortable, so there's a standard. Jim from Cardinal Glass is going to talk a little more about this to give you just a brief overview. There's these, it's filled with these acronyms. Like engineers love acronyms. CLOES for clothing units, right? I'm wearing like probably a 1.1 clothing unit right now. And the next one is actually an insulative clothing ensemble unit. Because, you know, it's not just this, I could have a jacket, I could have a whole ensemble. And they quantify that. They've quantified socks, slacks, jackets, hats. I think you talk about that a little. No, you talk about the net. So the net has to do with my metabolism, right? It's a very important factor in my comfort is what's my metabolic rate? I'm standing, I'm talking, I'm very active. I think we know that we burn about, like I'm a 100-watt bulb all the time. That's the rate of energy we can get, all of you are. 100 watts, right? 100 joules per second leaving your body. When getting back to that metal building, right? So we see metal and glass buildings in our world all the time, but rarely in a home environment, like an airport or a lobby or something like that. When you're in those spaces, you're active, you're dressed. You might not notice it as much as if you wake up first thing in the morning and come out to get your cup of coffee if there's a lot of radiant exchange. So the big one at the bottom there, PPD, stands for percent of people dissatisfied, and it is a curve that we're going to see now. So the problem is we need to go from qualitative assessment of, yeah, I'm comfortable, to quantitative, something quantitative and predictive, right? We're dealing with this implicit subjectivity, right? What we end up doing is we rely on the fact that people know when they're comfortable. So we put people in the chambers, we vary the conditions, and we ask them, are they comfortable? And from that, you can generate curves like this. So the black line, notice it's Gaussian, right? All natural systems end up being Gaussian. The size of leaves, the phases of the moon, tides. We are a natural system. What we have here is this curve stands for a certain metabolic rate, a certain clothing, and a certain set of indoor conditions, temperature, humidity, airspeed. And then you generate that curve, and it's PPD, it's the percent people dissatisfied. As Jim very cleverly pointed out, the engineers were not marketing people, right? You don't want to just talk about people being dissatisfied. They could have called it percent satisfied, but for some reason they went with the negative. So because it's a negative, you don't want very much of it. That means you would like to be down here. The lowest you can be is a 5%. So that means if there's 100 people in the room, 5 of them, statistically speaking, are going to be uncomfortable. So there's about 20 of us here. One of you, statistically speaking, is probably uncomfortable, according to this chart. And Jim talks about this chart a little bit. Coming up with his talk. So things like the Fitbit, these biometric sensors that we have, they might change this. They might be able to be, they don't yet, but they might be able to come into the thermal comfort standards and say, oh, sir, instead of guessing whether you're comfortable or not, I'm measuring your metabolism. I'm measuring your skin temperature. I know when you're overheating. I know when you're cold. So that's coming attractions probably. So as a building science consultant, I don't think this can be said enough. The enclosure needs to do the heavy lifting, right? The enclosure needs to do the heavy lifting. It is the, right, we know what it does. It creates separation of indoor and outdoor environments, and it controls the exchange. If Why is it so important? Because the enclosure is the HVAC system, right? In the sense of, what are we conditioning? If you ask most people, what does the HVAC system do? Well, HVAC, what's it stand for? Heating, ventilation, and air conditioning. It says it right there. It heats the air. It cools the air. It dries the air. We need to be remembering that as an industry, we need to be conditioning the people. We need to heat the occupants, make sure the occupants are cool when they need to be. And if you look at some of the factors, this is actually table 1 out of the ASHRAE standard. So ignore the ones on the bottom that say personal factors. We're going to assume that you can't control what they're wearing and what they're doing. But then you have general and localized factors. Only these two, humidity and airspeed, are not directly a function of the design of the enclosure. And a big hint is, well, thermonuclear fusion, you're going to control radiation. Well, that's what we're dealing with. So radiation control devices is a high dollar way to say shading, orientation, controlling aperture, controlling at the most basic level the window to wall ratio. Right? So make sure we remember that what we're doing is we're conditioning the people in the space. And we're exiting this era of machines to control air conditions, right? Now we're getting directly at the human factors, the people that are in there. So mean radiant temperature, mean in that word, in that phrase means average. Well, it doesn't quite mean average, it means the center, half above and half below. No, that's mean, no, it means average, excuse me. Take that back. So radiant temperature means we're quantifying the effect of radiant energy exchange on the people. There's two ways to define it. Well, there's three actually. And what we have is showing is the most crude and the least crude we'll illustrate next. The most crude, it says, let me go to the center of this room, a standing person, and we happen to define a person as where the center of mass is, which is right about here. And we're going to reference everything to that spot in the room. And we're going to do an area weighted average of this wall temperature, the floor temperature, the ceiling temperature, this area of the floor that's being heated by the window itself. Bring that is the crude way to do mean radiant temperature, area weighted average. The next one is with the aperture method, and it really depends on which chair in that room you take. Are you sitting on this chair up close to the screen, where the fireplace is, or are you sitting on the far end of the couch close to the glazing? It's snowing outside. So where you sit makes a big difference because of the angle view factor, the aperture. The blue pie pieces here, right? You can see what's happening is, as you move this way, this guy who's seated is getting closer to the window. As he gets closer to the window, he and the window are more radiantly coupled. So this is something that's implemented, and I think Jim shows a little bit of it in the X-ray thermal comfort tool. It's called the angle view method, or angle view factors. So mean radiant temperature can be calculated. So we can define for a space the mean radiant temperature. And from that, we can define what's called the effective temperature or the operative temperature. The operative temperature is what the occupant's thermal experience is going to be. And the reason there's a seesaw there is because we really want the operative temperature to be stable. And for certain conditions, under certain conditions, which is reasonable window to wall ratio, is probably 35% or less, and good solar control, this equation is valid. It just gets more complicated for the math, but the operative temperature is always a combination of the air temperature and the mean radiant temperature. So you remember we said thermal comfort is not a good proxy for environmental quality. Air temperature is not a good proxy for human comfort. Right? Mean radiant temperature is actually dominant because that's how our body want to control it. So if the mean radiant temperature goes up, then the air temperature needs to go down, which is common here in the summertime. That's what we're going to see. On things like these psychrometric charts that we see all the time, it's actually the operative temperature, not the air temperature that's at the bottom. There are certain conditions where you can say, well, assuming the inside walls of my space are held at air temperature, then I can call them equivalent. It's not usually the case that assumption is a valid assumption to make. It is usually the case that assumption is made as though it's valid. So psychrometric charts can be used incorrectly. So I'm coming to my wrap up now. 5 main points. Sunlight, when you let it in, and you want to let it in some sense, right? You gotta let it in carefully. It downshifts the heat. I'm ignoring, by the way, their visual effects here. Once it's in, something's gonna get hot. There's no undoing it once that heat is in the building. Air temperature is not a good proxy for comfort, right? We need to combine it with radiant temperature to make sure the operative temperature is good. A design shop like us, when we see a highly glazed zone, we calculate the operative temperature. We calculate the mean radiant temperature, and then we'll change the set point in that zone to the air temperature. So instead of being 75, it's probably going to be 72. If there's more glazing, 68, something like that. And this last one, point 5, is that quality and performance are increasing in our buildings. To make a beautiful building today, it's definitely starting to mean that you understand the unseen forms you're working with, the thermal comfort factors and the visual comfort factors that we'll talk about next. So I will pull up Jim's talk, and he's going to talk to you about window thermal comfort.
Well, I guess I could say good afternoon now.
Let's start your introduction.
What?
This is Jim Larson, Cardinal Glass. He's in mechanical engineering. He's been working at Cardinal for 30 years.
35.
He knows a thing or two about glazing.
Haven't figured out what I do yet, so that's as long as nobody catches me on.
And he flew into town for this. We really need to thank him for that. And so, any questions you think you ever had a question about glazing, ask it.
So maybe a quick description on my title here. I used to be an engineer, and now I go out and try to teach this stuff. But I've had a great history with the company in developing products, running a factory and building products, and now spending the last 15 years training, working on building energy codes, and just trying to advance the science on windows. Quick thing here on who Cardinal is that we're a national glass supplier. We've got 38 factories. There's like, I always have to recount. I can't figure out where they all are. They're all in the lower 48. We're the biggest glass supplier to Canada, but we don't manufacture anything there. So there's a lot of diesel fuel involved in our infrastructure here. But we got the 4 primary divisions is that we melt sand and make glass. And then we sputter OE coatings to make coated glass. We can take those products and fabricate it into laminated, so that's like the windshield in your car. That's what's used for a hurricane impact in particular. That's really moved that market ahead. And the insulating glass is the double pane unit then. Now, from a history perspective, we actually reverse integrated. We were first and foremost an IG company. And then we got into the low E business as a way to improve the thermal performance of that insulating glass unit and having something more definitive to sell to our customers. Then along the way, we found out is that you need really good glass substrates to put coatings on. And we weren't exactly getting that from the other glass companies because they perceived us as being a competitor. So we actually ended up going backwards here to make ourselves fully integrated and build glass blown plants and melt sand and do all of that. So today we're the largest manufacturer of low E and insulating glass, at least in the US, probably in the world when it comes to low E in general. You likely don't hear our name that much because we don't focus on architectural too much. We focus on windows. So it's more of a residential perspective or a punched opening, you should say. Is it we will do curtain wall jobs, but we don't have a sales force that goes out and actively pursues jobs. We work with manufacturers. We have ongoing relationships with those manufacturers and get to the market that way. Okay, enough on Cardinal. Now the NFRC window labels. Everybody recognize this? It's on every window you sell, right? Every job you do. Well, I would hope it is because that's a code requirement. If you do not have this label, what you have is single pane, double pane, clear, or tinted. That's it. That's what the code says. That's the only thing that you can claim without that label. And none of the values for the defaults for that are code compliant. So just as a refresher for everybody is that it's important to have that information there because a lot of what you get in the window frames, the glazing technologies, and the materials that are available, you can't see. It's embedded into the product. Low E coatings, excuse me, transmissive in different spectrums, what have you. So let's go quickly here to the values that are on this chart. U factor is the measure of air-to-air heat loss. that's the value you want to know for, could you give me a last one? Excuse me. That's what you gotta worry about in the cold, in the heating season. It's the amount of heat that transfers through the window at that time. Solar heating coefficient is just that. It's 0 or 1. An opaque wall is 0. An open window is 1. And that's just a relative ranking between them. Visible transmittance, we'll get into that. You're talking about the the glare aspects and what have you there. The important thing to understand for all of these values here is that these are whole window properties. The performance of a metal window with a low coating is different than the performance of a vinyl window with a low coating. And so it's representing the integration of a whole window product. So it's talking about what's the hole in the wall and what am I putting in there in terms of the heat transfer characteristics there. Okay, we saw this a little bit before. This is standard 55 is the procedure. It's actually has its roots from 30 some years ago. A lot of research that's gone into the physiology of people and the dynamics of their response and what have you. Out of this, we pick up a couple of points here. As Christoph was telling us, is that it expresses satisfaction, and you can't satisfy everyone at once. We know that. We all have customers, right? You can't satisfy them all. But I think the process that they've gone through is statistical analysis. Is that for a particular set of conditions, you might satisfy, let's pick a number, 80% of the people, and they'd be happy with that space. But what you want to understand is that, what if I change the conditions? What if I put better glass in? And now I satisfy 90% of the people. The important thing is that what direction are we moving in, and where are we pushing the response on? So I tend not to get too fixated on the absolute value that you're calculating at that particular time, but what's the comparative measure of the different scenarios that you might compare. So there's this 7-point comfort scale going from damn cold way on the left here to damn hot, and a little bit in between there. And what we want to do is be in that sweet spot in the middle, near that neutral point there. You might be vary a little bit, between slightly cold and slightly warm, but that's what you'd like your building design to have. That's what you want to be able to give to your customers is something within that realm. We saw this, so if anybody doubts that there's science behind this, look at this. We got a fourth power equation and the exponential on top of that fourth power. It's got to be science, right? You got to put it into a spreadsheet to generate that curve. Well, the thing that I like to do here, and these colors unfortunately really overlay that scale, which is exactly the same thing that's down on the bottom, so that over to the left, the light blue is that you're cool. To the right, you're warm, and we're ideally wanting to be in sort of this kind of range there, into that neutral. A comfort model. So it does all that math for you, and it gives you a result for one particular condition. So now it becomes a question is, what conditions do you pick? How are the people dressed? What's their metabolic rate? What's the temperatures? All these other details in there. But they've got some choices in here on metabolic rates. I'll give you some quick examples here. You go from walking, you already caught it. There's a, relaxed, standing, seated, quiet, sleeping, all the way down to dead. I don't know why dead doesn't have a 0 metabolic rate, but Christoph said maybe there's some outgassing going on here. There's still some decomposition or something. But you can take that and take a look at what each of those metabolic rates affect just from a 70-degree room space and what your comfort level is.
And that's mean and air temperature at 7.
Yes. Yep. So in this first step here, so let's say you're walking at 2 miles an hour, the person's going to be slightly warm. So it's 14% dissatisfaction level. I'm going to back up here and look at the curve. So what we've got is you're slightly warm, you're 14%, you're somewhere about in there. You're starting off on that side of the curve, your activity level is compensating for what the rest of that space feels like. So if you are designing for exercise facility for Eskimos, you're going to have to use slightly different interior design conditions to create your comfort level. So you can account for all of that as you go through the process. So here we're slightly warm. We go to standing or relaxed, and you get into a neutral position here. Is that you've shifted over to the left a little bit, not quite as much activity, but you're comfortable at that space. Slow down a little bit more, and now you're sitting and not really doing much of anything, kind of like all but one of us in this room right now. And you could end up being slightly cool under those conditions. Take it to sleeping, and if you don't throw a blanket over the top of yourself, or do something there to compensate for some other physical activity and laying down, and you're going to end up being cold, and obviously you're damn cold, even when you're outgassed. So you can go through the program here. It gives you these nice little icons here for different clothing levels. This is where I wanted to jump. If you want to. And it's very politically correct. You can't go to 0. It actually won't allow you to type in anything lower than 0.1. That's right. Okay, so you go into this standard, into 55, and it then says that they're going to do the evaluations under some standard conditions. And what they've selected is about what you got right here. You're in an office space. You're seated, you're quiet, and there's not much for extra activity going on, but then recognizing that we adapt our clothing level during the season. In the wintertime, when it's cooler, when the spaces are cooler, we're going to tend to put on a sweater, put on a jacket, have an extra layer or so on there. In the summertime, end up being shorter sleeves and less layers there. You generally would use the thermostat. Presume that the equipment is holding temperature in the space. You can use that as the surrogate for the air temperature. Then you have to do an MRT analysis. That's the mean radiant temperature. This gets to be really complex because as Christoph was showing us, you're doing these view factors to all these different components of the space. The good news is the program will do that for you in the background. You can take, in this example here, I said that on wall 4, over there on the left-hand side, there's a window that's 6 foot by 6 foot, and the surface temperature of that window is 44 degrees. So it will actually take and calculate the MRT for that person. In this case, I think that's 3 foot away from the space, from the window. It'll calculate that view factor and that MRT and finish off that comfort analysis for you. Plug that all back into the program, and I don't remember what the particular set of conditions were here, but in this example, whatever is it, I got 21% dissatisfaction level. PMV is minus 0.9 roughly. So you go in and change your conditions. Raise the thermostat, change the activity level, and you look at the comparative difference there for the response. A couple of quick examples. Efficientwindows.org is a great website that's got a lot of comparative information on there for different window systems. So you can pull up things like this, you can do energy analysis, you can do whole year comfort analysis off of that. But look at the importance of this particular chart here. So let's say it's 0 degrees outside, single pane clear glass, probably 60% of the people are going to be dissatisfied being near that single pane window. Why? It's damn cold. And you don't want to be exposed to that cold glass surface. Just a simple act of going to double pane clear glass. We'll cut that dissatisfaction level in half. Now I take that double pane unit and add a low E coating to it, make it a better insulator. The window will be warmer at night, and we see a further shift in that. So again, this is the engineers here working backwards. We're more better because we're less discomfortable. We have to understand that the logic behind this. And you can go all the way down to triple pane unit with the 2 low E. Okay. So what standard 55 doesn't do is it doesn't give us any solar input. That's something that I don't even know if they have any plans to get to that into the future, but I've worked that through in some analysis. The background for this work has come from Lawrence Berkeley Labs. And here's the essence of what happens. We've seen this curve before, but what if you started slightly cool and add sun to the space? I think this all makes sense to us, is that as you add sun, you're going to shift over towards a warmer feeling with that direct sun on you. That's great during the time that you're cool, but what if you're neutral? If you're in a condition where you're fairly neutral, now you're going to move over into the slightly warm condition. If you're starting to slightly warm, that same level of radiation is going to shift you over into the warm. So passive solar is a great concept. I'll take a little bit of a tweak on what Christoph said on that perfect glass for the cold weather climates, is that it used to be, it was nothing but high solar gain, low E in the north, and the people complained like mad. Not because of the nighttime performance, but because of the daytime performance. And it was pushing back on the window manufacturer saying, well, you told me this was comfortable all year round. It was better performance all year round. And I'm sitting in my west-facing living room and I'm broiling. Well, their senses weren't lying to them. The glass was allowing that sun to come in. While it was beneficial during the cold 3 months of the winter, that was fine. But any other time of the year, it's not desirable. So you have to be cautious in how far you take the argument. You can do the same kind of thing on these discomfort things that I'm showing you there. There's 2 aspects that you can have from comfort, discomfort there. One is direct sunlight impinging on you. And the other would be for the glass getting hot. A lot of the glass technologies, what's called some of the tinted glasses in particular, they're absorb solar energy, and they get hot in the sunlight. And so you're getting sort of this double effect that whatever sunlight comes through there, you get hit and you feel that, you sense it, and then you feel the heat off of that glass surface as well. So you got to be cautious here as to what particular products you're comparing. So let's take all of this as background here and expand it into a more detailed analysis. I'm going to use those ASHRAE standard conditions for the clothing level and the MRT. Assume the person's about 3 foot away from a medium-sized window, and draw a number out of the air and say that let's set the comfort threshold of the space as being 10% above the space without windows. That's my line in the sand. If you want to pick another line in the sand, we can go ahead and do that and then rerun the analysis. And I'm going to do 2 conditions. I'm going to do winter night, and then I'm going to do south phase or summer west phase. west face, and then I'm gonna do the full year weather data set. And that's what's unique about this, is that looking at 8,760 hours of data. So I got a grouping of 20 different window systems. Got metal windows, metal thermal break, non-metal, triple panes, low heat coatings, high and low solar heat gain, so the whole gamut here on different performances. When I go through the winter time performance, that winter night performance, this here being the U factor. This is going from single pane glass down here, to super insulating product all the way over here on the right or left. So what you see here for 3 different climates, I did Houston, okay, it was a 4th of July weekend, right? I have data for Austin, I got lazy and Houston will graph. I figured Houston's close enough. But what you see is that, big differences in the response. Hours of discomfort is a function of U factor. So if you're in a cold climate like Minneapolis, is that it looks like you want something that's down around a 0.2 U factor is a way to get to the level where there's not going to be any thermal discomfort. Come back to this part of the world and maybe 0.4, 0.5. So that's a big difference in the selection of window that would make you comfortable with. And then I can map this out against that 20 window sets, and you notice the 2 big peaks there are single pane glass. The one over to the left is a metal frame. The one over to the right is a non-metal frame. So in this case, it doesn't make any difference whether it's metal or vinyl. It's single pane glass. It defaults to that metal glass in front of me. So if I repeat it for the hot weather side, not quite as much separation. I always like to say that Kansas City is kind of like the worst of all worlds. On the north, it's connected to Minneapolis by I-35, so it sees all the cold that Minneapolis gets. And the south, it's connected to, this part of the world, it sees all the hot that you get. So they do have some real extremes there. And you see that Kansas City looks quite similar in terms of the summertime. But this is solar heat gain on the bottom scale. So high solar heat gain to the right, lower solar heat gain to the left there. And this is where it graphs out here. So I wanted to point out where you get to the neutral positions here. These are low solar gain, low heat. These are windows that are getting down around 0.2 solar heat gain. You see there, it doesn't make any difference what the frame is, because the glass so dominates the solar gain side. The frame is opaque. But regardless of what you put into any of the higher solar heat gain products or what frame you use, is that it doesn't really shift the ranking underneath those.
And I want to point out that this is for people with wearing clothes, like office clothing, and not much activity. But if they didn't just wake up in the morning and stumble out of bed into these environments, so things would shift if we had different units.
And so, I mean, I could give you 1,000 snapshots of this for all the conditions that you want. But it's going to be this comparative analysis then across these 20 glazing options. And I know that in the solar one in particular, it's going to follow this same basic pattern. So, conclusions here is that while we didn't cover it much, is that size matters. You're going to have a very different comfort perspective in that space out there with big windows as opposed to this space here, just because of the radiant coupling that you have with those. Location matters. If you're in a northern latitude, you really got to focus on those U factors. As I mentioned, Kansas City kind of gets a little bit of the worst of both. Interesting is that summer extremes, air conditioner sizing in Minot, North Dakota is the same as it is in Miami. Now, you might only run the air conditioner 1 or 2 days a year in Minot, but that one day it might not as damn hot. And so you have to, understand some of those variations, and then the idea of the orientation complexity. Passive solar benefits are there, they are real on the south face of the building, but be careful when overextending those benefits to any other elevation. You need to analyze them separately.
Thank you.
Okay.
Okay, so. You want to put your computer?
Yeah.
Okay, so thank you guys for sticking around. This is Matthew Tanteri here for training. Who's seen him talk before? Me? I've seen him several times. If you guys want to invite him for a lunch and learn, maybe. We're good on. So he's a fellow with the Illumination Engineering Society.
We're good on time here, there's nothing following, so.
You guys, this thing will keep going.
Yeah, we're good.
Cater, part of Cooper Union, other places. Parsons. Parsons.
Was it for 14 years teaching? I still teach at Cooper Union. And I'm a daylighting and lighting consultant. I moved here from New York. So I laser pointed one out. Alright, so I want to start off with a public service announcement. So I got this morning, it was from my local Cedar Park hospital saying how to avoid heat-related illness, which is drink lots of water, don't drink alcohol and caffeine. And then go visit an air-conditioned location. So this is pretty much when the temperature goes over 100. So here's the different scenarios for the 3 different global warming, like how many more days over 100-degree weather we're going to have, and it's depending on which scenario we follow. But you can see we're right in the part with the dark red colors, where we're going to be adding on somewhere between 80 and 100 days of more over 100-degree weather. So what's it going to do? The solution is it's going to drive people indoors. The solution is to go indoors, because it'll be really hard to be outside when it's 120 degrees day after day. So it just, to me, this is like the commercial in RoboCop, when the RoboCop series is on. Harsh reality is coming true, in that we're getting to these high degree, it's going to be hot outside, we're going to have high exposure, and we're going to be driven indoors. So that was my little public service.
So make the indoors comfortable, because we're going to be living in them.
So I worked with the title of this lecture, and I settled on this, that it's about Windows comfort-based design, more from a visual standpoint. And it's really climate-based design, but I'm substituting occupant-based for climate. But this is really a rehash of climate-based design. So I want to start off with just saying some simple things that the last two speakers have said, which is that comfort is at the core of good building design. When I say good building design, I mean best practice building design, what today's profession considers best practice.
Which is integrated design.
Comfort qualifies both the performance of the building and the experience of the building. So it's the metric that links the occupant and the building. You've probably heard, maybe Christoph has said, we don't design for buildings, we design for occupants. But I think the reality is we design for both, right? The client wants the building, and today we design for performance, but that performance has to be occupant-based. It's not just the building saving energy. Comfort is what makes the performance base more towards the occupant.
Mm-hmm.
Design, when you design, you can prioritize any one factor. Right? You can choose any one of these factors to make your building have that as the main goal. Or you cannot have any factor, and you just get what you get. Or, as you go through your design process, different iterations, you can keep comfort as your main goal. So even though you start off with a design and a goal and your priority has to be number one. So even if you go and start looking at aesthetics or low energy use, keep comfort in the iteration. You go back and look at So Christoph and I were talking about comfort a lot, and there's really two aspects of comfort, right? There's this thermal side and the visual side. So I'm going to talk about some of the analogs. Well, the first is that thermal comfort is the subjective experience that has a lot of separate, has constituent elements and separate things that have to come together to make up this subjective impression. So I was at Port O'Connor on Saturday, and why are people here? It's so hot, it's 100 degrees, it's actually a cool day there. But you know what? I was in the breeze and I was so comfortable, and I said to myself, I gotta get rid of this idea that comfort is being in motionless air that is of a certain temperature.
Right.
It is delightful to be in warm, moist air when it's moving. It's one of these feelings of delight. In the same way, visual comfort involves separate elements that we have to look at together and look at the subjective impression of them. So that's what I'm really going to focus on, is the visual side. And the reason why we're talking about windows is because windows are the main element of the fenestration of the envelope assembly, where all these things come together, right? So this is showing convection. You know, it's the temperature of the window controlling air currents. There's a heating element below the window. But I'm going to talk about the visual side, but this is just showing you that there's all these things, visual and thermal concerns come together at the window, and there's several energy transfer mechanisms that are involved there. And if you just look at, when you start to analyze that for visual and thermal comfort, you may use the same input data. You're going to use a dynamic climate data set, typical meteorological year, TMY. But you're going to use different software and you're going to have different results. But you start off with the same software. So even though you solve for energy, doesn't mean you solve for comfort. You know? And so you have to look beyond energy to get a complete picture. And this is non-trivial because it's parametric analysis. In visual comfort, sometimes we're just trying to find out the most simplest thing, which is when will the occupant open and close the shade? And that's very difficult because occupants tend to close the shade and never open it. And they defeat everything, right? If you design this beautifully daylit building, once the shade's down, everything's gone. But it's so difficult, like all the experts now are meeting again to come up with new glare metrics because, you know, there's predictable things, like if you have latitude, you can figure out solar path. You couple that with building geometry, you know what the sun, what direct sun hits inside the building. All the stochastic elements, which are unpredictable, that's all your outdoor climate parameters, which you can use representative data, but it doesn't tell you exactly what's going on each day. They're just, and climate changes. But then this is the hard one, behavioral data. Like, how do you know the differences between what one person likes and another doesn't like, in terms of their temperature preferences, or what view they like, or where they sit, or how much they get up and get down, what their metabolic rate is, or what their adaptive state is. Where were they before they came in the room? How long have they been sitting there? So it's non-trivial and requires parametric analysis. So just to round up the key points of this first part is that comfort is at the core of best practice building design. It links the performance of the building with the experience of the occupant. You can decouple comfort into visual and thermal concerns. The reason why we're talking about fenestration is because that's the area of major energy flow where these two come together. Both the analysis of thermal and visual use the same set of data, but you get different results, and we need parametric analysis. So let's go back to that irradiance, this chart of how radiation from the sun gets to Earth. Like this is extraterrestrial before it gets through the atmosphere of the black line. Now, what's great about this particular chart is it divides up radiation into what comes from the sky, which is blue, and what comes from the sky and the sun, which is red on the horizontal surface, and what comes from the sun on this plane that tracks the sun, which is yellow. That's very important because when we want to start doing intelligent things with understanding data, we want to know what these different levels are. I'm just going to go to, on a clear day in July, we've got about 1,000 watts per square meter. About 945 watts per square meter comes from the sun, and about 80 comes from the sky. So I brought my tools to Port O'Connor. this past weekend, and I took out my foot candle meter and I had over 10,000 foot candles. That's a huge amount of light. And I had close to 1,000 watts per square meter. All right, so you can directly convert this into 307 BTUs per hour per square foot. And I'm going to make you feel what that is indoors, because part of what I want to do is give you a tangible feeling for all this, for heat and light. That was my goal today, was to give you a couple of hands-on demos. First, I'm going to tell a little story. It's what my mother used to tell me when I was young, and she saw I wasn't getting too tall or wasn't looking too pretty. So she said, Matthew, don't worry. It doesn't matter what's outside. It's what inside that counts. So I know she wasn't. I know she was trying to make me feel good, because I know it's not totally true. Let me give you this little story here about this building. So we know what this is, right? It's a Stirling engine. It's a parabola that takes sunlight, focuses onto that device in the front. Turn it upside down, and it's not unlike a building that Christoph just saw on his visit to London, which they call the radiator building. Because this building, for 2 hours on 2 days of the year, it focuses sunlight down onto the area of London, and it burned a Jaguar XJ. And so I know the architect well, I've worked with him. So what did he say? One problem that happens in this town is the superabundance of consultancies and sub-consultancies that dilute the responsibility of the designer to the point that you just don't know where you are anymore. Now that, I'm concerned about that, because this is something that I would consult on, right? So I have to know that's an area of liability for me, is knowing that reflected light. What did the developer say? The developer said that the problem is the current elevation of the sun. It has nothing to do with the building. These are actual quotes.
The sun is in the wrong spot.
The architect said, didn't realize it would be so hot. When I first came to London years ago, it wasn't like this. Now you have all these sunny days, so you should blame this thing on global warming. Okay?
It was 94 degrees and sunny when I was in London.
So as litigation started for this, one of the things he said was, I knew this was going to happen, because it happened on a previous project he did, but there was a lack of tools or software that could be used to analyze the problem accurately. So I'm just showing you the simulation that analyzes it accurately. Of course, someone showed no there is. And it's showing how the temperature on the little rear view mirror on August 29th for 2 hours goes up to 214 degrees. All right? So that, whenever you have one of these things, that's what it did to the rear view mirror. This is the picture of Martin Lindsay when he came back and found it. Someone snapped a picture of him. Like, it also burned the molding on the side of the car.
It changed.
And then someone always goes with an egg and fries it in a place like this. Like in New York, someone always would do this when there was a hot spot. And this is the picture of the fried egg. And it shows that egg white coagulates at 144 and the yolk at 149. And they found, in general, you can find 140. So they found that spot was that hot, which is a black tile. All right, here's the building. Here's the building. What's the solution? Well, here they showed it with scaffolding built on it. This is the solution. You cover the grease layer. So all the money spent on this building, what was the problem? Well, the problem was they built a solar reflector. So how do you fix it? Well, it's like when I bought my son this magnifying glass, and I said, be careful, don't burn anything. They took out the little point that focuses the sun. You can't focus this. So there's the solution. You don't build buildings that focus, right? When you build a concave surface. And we've had a similar, so this building was about thermal discomfort, because it burned things, it melted things. You can't get more discomfort than melting something, burning something. And you've had the problem here in Dallas with the Museum Tower, which was a convex surface, which was about glare. The Nasher Sculpture Center had this nice brise-soleil, and then they built the tower behind it. Now it sends sunlight down to also all the artwork. And the president of the AIA in Dallas wrote this beautiful letter, which said, it's a beautiful letter, you gotta read it and download it. The Dallas building code was going to be changed to limit exterior flaggings to 15%. So you couldn't have any glazing that was over 15%. And he had some beautiful rebuttal points in there, which was, it goes beyond reflectance issue, it's a larger issue. If you make any glazing over 15% unusable from 258 glazing options, we only have 8 left when you consider ATEU values, soaking coefficient, and exterior reflectance. So the point is for this is don't make mistakes because they impact the profession. So here's my key point, my little story here, which was radiant energy flowing from this end contains high levels of light and heat. Not addressing the impact of building form and fenestration can result in severe visual and thermal discomfort. Mistakes impact the profession and probably your insurance rate as well, the liability insurance. So here's, let me just get to the meat of what I'm
Could have
talking
put the
about.
Aqua Tower in Chicago on this list as well. I'm sure you've made that famous.
So here's what the meat of the presentation. It's called glare, right? This one, what is glare? Okay, so to talk about glare, we're going to start with this Chinese proverb, which is, we're going to call things by their right names, because that's, to understand glare, we have to understand some basic lighting terminology. And that is that most of us talk about illuminance. Illuminance is when a light ray comes to a surface. You take a light meter and it's a light ray coming to a surface. That's incident upon. That's illuminance that we measure in foot candles or lux. Then, so that's the ray coming this way. Then that ray hits something and leaves the surface. It's reflected by the surface. Well, that's luminance. That's what we can measure. Like when we measure luminance, we're measuring light leaving a surface or leaving a light source. So that we measure with a luminance meter, which is this thing. This is a luminance meter. This is an illuminance meter. This is the irradiance meter. But that still doesn't tell us about glare. Glare is brightness. It's related to brightness, and brightness is a subjective impression which has no units. It's how we can say something's bright or dim. That's really the metrics for it. So let's look at what this means. So the human eye is incredible. It can see 12 orders of magnitude brightness. It can start off with this absolute threshold of vision down here, which is scotopic is night vision, and then it goes all the way up to this red box here, which is 300,000 candelas per meter squared, which is the upper limit of visual tolerance. And then in this blue box is all the daylight level light sources that we see. So, and you can see that in an indoor environment, we're starting to bring daytime levels indoor. Like most daytime level light sources, luminances are between like single 3 to under 1,000 candelas per meter squared. So just to give you some reference for this, this is the upper limit of visual tolerance. This is the most you can look at and be okay. You can't look at it a long time. Actually, it starts to leave an after image, right? But you start to go above this, you know, you can see where you start to get into possible retinal damage looking at the sun. And if I want to measure it to give you, so you have a reference for about 300,000 candelas per meter squared. Now, if I look outside, let's take a guess as to what's the luminance here, you think? Just look at my chart.
And that's 300,000?
Yeah, that's 300, that's about 250. But what's that wall?
That's
18. So you see how comfortable you are with 18? This is about the level, you know, from like single digits into the hundreds about interior light levels. That's because the combination of daylight levels with most surfaces, which are 50%, around 50% reflective, you end up with values like that. Now, how about outside? Looking through that shade, take a guess at what the light level is out there.
compared to like 5,000.
Look at the chart. And I'm saying to you that indoors stays under 1,000, It's somewhere single digits. And I'll give you this little thing too that we try, glare starts to happen over 2,500 candelas per meter squared. That's your maximum level. So what do you think, are you comfortable looking outside?
Yeah.
You are, right? Okay, well, it's about 110 out there. Let's,
It's not bright from this angle.
shirts.
Just, you can turn this off, you guys? That'd be great.
Hey, look, I'm going to, okay, all right, now I'm gonna look at with the shade up, it's going to close to 1,000. Now, I have my subject out there with the mirror and it's partly cloudy. So what we're going to do is we're going to wait till he reflects a ray of sunlight in here. We're going to see, take a guess as to how much a ray of sunlight would be a sun patch. No, it's still getting bright. It's still cloudy, so there's no. But this has been going on every 5 minutes. So
There it is.
It's a very okay. So as we talk, we're gonna keep going. When it happens, I'll be good. So glare involves a number of elements. These are the major dimensions of glare. It's the luminance of the glare source, the size of the glare source, the seen luminance, and the position index. This is our binocular vision, our small area of vision.
There it is.
Take a guess. Reflected sunlight. Take a guess. Out of all the things I've said to you,
You said that was 18,000 there?
I said over 2,500 it starts to be glary.
That's too bright.
That was 30. It was equal to this.
That was 300. So it's also hot.
That was 300. Yeah.
Yeah, so it's definitely hot.
Yes, it's hot. Right there. There's 30.
The idea of
380.
heat and light. 380.
So that is I wanted to show you that just so you can place it in that chart. So these are the different elements you have to deal with glare. There's different glare metrics that create algorithms of each of those things. If I want to give you a basic formula for glare, it's not to exceed 2,500 candelas per meter squared anywhere in the window. Don't exceed 10 to 1 between your window and the surround. And this is based on a computer screen is 250 candelas per meter squared. And you don't want to have greater than 10 to 1 with the surround. So that's what it's based on. It's really based on office environment. But it's very, it still works in a residential setting. So because if you experience discomfort the same way. So we can quantify glare. And it's very easy when we look at Austin's climate data and we see when the major the radiation happens through the year, when we exceed the comfort zone here, the bandwidth of comfort, that there's ways to control that. If we have a building and we break down the amount of radiation on each vertical surface, so that's what this does. This is what's exposed to the south, east, north, right? So this is the morning exposure from 6 a.m. to noon. This is west from noon to 6. You can see north, you just have a little in the morning and afternoon. South is the two humps when the sun's low. You know, it's hot, it's not hitting the south so much at a normal angle. So what you can do is you can put sensors on each window and trigger shading based on BTU or the luminance. And that's what the new trend is. And for me, that's happening in residential. That's what I'm pushing residential because it's very easy to do. And you can decide what the triggers are, whether it's light or heat. And you can couple it to temperature, and we can go look at comfort algorithms, but we can and adjust it. And if you want to be more intelligent about it, you could take this device that measures irradiance and put this on the roof. And if you remember that if the level goes above the sky, then the sun is out, then you don't need to put one in every orientation. If you have a computer model and you know when the sun should be incident on each of the sides of the building, all you need to know is when the sun is out, because you can run a computer software that knows when it's sunrise and sunset. The only thing it won't know is when it's cloudy and when it's sunny, like today, right? With the sun going in and out behind the clouds. But if you read just this level, like this particular wavelength area, and see when this rises above, you know that the only way it's going to go up into this area is if the sun is out. That's when you can draw a shape. So what I think the three speakers have, I'm at the end here, what I've seen with all of them, to divide, so dealing with the window involves letting in daylight and providing view. These are the two functions that have to be interior fenestration design. I drew up some different typologies for windows for residential. So here, the top row is all curtain wall ideas. So here's the curtain wall idea where you drive a view shade up and down, but you always leave it up a certain amount. That's your source of daylight. This light reflected off the floor, it's an interior light shelf. And Christoph and I are talking about removing heat from this area to make this room more comfortable.
Radiance. What's the red dot?
The red dot is a sensor, right? And then here's a variant of it. You have a diffuser shade that's top down and a view shade that's bottom up, and you use the diffuser shade to get your light source. It's like having a piece of translucent glass. And when the sun's not there, you can pull the diffuser shade out. But now you have view and you have daylight. And if there's a sun patch on your window, you can control the sun patch by having a diffuser shade right up and down. So you're really working the two shades together. Then you can have an overhang, and you can just use all reflected light as your light source and pull your bottom up view shade so you always have a view out. Basically like the way this is, except what this room is, except you have a portion that's not shaded above to get light to bounce deeper into the room. So that's a curtain wall solution in a residential application. Here's punch windows. This is a similar idea where you're just leaving a space above, below the view shade to let light in. I've also that light, so I've cut the little corner off of this window opening. So that's another little technique. On both sides I've done that. Here I've driven the diffuser shade with it, similar to that. And then here I've just shown more of a vernacular canopy type on a residential punched window, but it's basically the same as this. So that's the same idea. All right, so that's how you can design windows for daylight and view and shading and have seasonal variation and
Without light shelves too.
without light shelves. Yeah, because light shelves don't look residential. Well, right? Here's some software that, this is a simulation. It's called a human sensitivity image because it takes the simulation, it puts it through filters that duplicates what your eye actually sees.
So that's not a photograph.
It's not a photograph, it's a simulation that takes what appears on the computer monitor and makes it what you would actually see. And here's an analysis of the luminance, which shows that everything's under 2,500 candelas per meter squared, and it puts it through this glare metric, which is daylight glare probability. It's 0.2, which means it's imperceptible glare. And so this would pass. So this was a design we did for a residence that faces the sea with this daylight window above. And this was the view looking into the room from the same room. And it shows that the only points that go above, like these points were starting to get into 3,900, but they're little, can be fixed because this was the little interstices of the trellis where sunlight was coming through. But this can be sparkle and pretty if it's small enough. So you may accept that. The thing with daylight is you can go for higher contrast levels because once you have view with daylight.
That's a simulation as well.
Yeah, that's a simulation. And then here's another variant. We took out the glass, the diffusion glass, and just used clear glass up there. And it still is all within, and we raise the shading device so that direct sunlight doesn't come in here. And now we're still within our visual comfort, it's just another solution. So the key points here is brightness is not the same as luminance. Brightness, right? Visual comfort involves the control of luminances, their size, their position, and intensity. You have to consider view and daylight together. The glazing and the shading specification, in combination with controls, can allow fenestration systems to adapt to the wide range of exterior luminances to the narrow range of the human visual system, right? So you can use your fenestration system to take this wide scope of luminances and bring them into what's comfortable. And that's where automation and sensors and the Internet of Things is coming. It's here. So the way you wear devices on your wrists, and there's devices you can put on your glasses that also measure light levels. We're moving towards that to have comfort. So that brings us to the little show and tell part of this, which is in the back. I'll invite you to the back. And we'll just refer to this. I'm going to bring this little tabletop back there, and I'll show you a couple of things. So we brought some of Jim Larson from Cardinal. Can you just pull that out, the piece of glass out? Could you want to take it back out? So come to the back room. Could you put the shades down too?
Okay. Right.
Jim, why don't you show that box? And then I'll show this thing.
So I've got 3 glass samples here. This would just be conventional double pane clear. This would be a medium solar gain low E, and this goes into a low solar gain low E. The interesting thing here is that when you look at these and view through, is that the one on the right is almost an 80% of solar heat gain. The one on the left, a little bit of drop in BT, but you're going to get a window at about 0.2.
So it's one of the, it's okay to use the numbers. So you guys know low E 366. It's 1340 and 1366.
No, this is 366. Yeah.
And the other one was
Clear.
just everything.
So it'll take us a little while, but the radiometer will just spin faster depending upon the glazing that you got there. And you can start playing around with, moving it from one position to the other. Usually there's some doubters in there and I have to switch them from one side to the other. Are some, I haven't checked these, some of the radiometers can get tweaked a little bit, and so you can get some differences in them, but I'm generally not trying to spin it.
So a lot of momentum on it.
So that one will now start to slow down because that's the,
Try stacking them. There's a lot of momentum, huh? It's got every kind of problem. 70 and this is 366. That should be
that's really slow.
Well, that's not.
We have the time to wait. There we go. It's flowing now.
When Robert was shining that sun in, it would go across me. It was so hot.
Yeah. It was really cold to be inside.
So why don't you do yours while this one's stabilized?
Well, what I wanted to, this reads, it starts at 100 watts per meter squared. It doesn't go below that, and it doesn't go below 30 BTUs. So when I was measuring this, I'll tell you what I was doing. I was measuring regular glass, and I was measuring, I got readings. But then when I measured your 366, I got no readings because it was below. But then, so I thought, well, what can I demonstrate with this? So one thing I figured out is that
Where's the sensor on the front there?
It's this. One thing I figured out is that, all right, so you would, I can hold the reading here, and just to show you that there's no reading, right? That 78 is 600. It's the top, see its old dashes, it means it's below the sensor level. But if you put this inside, and this is where,
So it's doing watts per meter squared, so it's rate of energy per square meter. And it converts it to BTs too.
I can have BT is 4 watts per square meter. But this is the 366.
So I don't understand what you're doing. What are you doing?
Well, I want to show you that the RAT equation, which is the heat doesn't just go nowhere, it's being reflected back into the box, right? If I take, which one is the best? One of these did. If I had the,
Well, 366 will be the most reflective, and I think you have to do it just the way you had it there.
Yeah.
Turn it this way, so it's now reflecting back at the mirror, but you have to have the mirror looking closer at the glass.
So you're saying low E 366 is bad because it's reflecting heat back into the
no, oh, I had it on hold.
Heating the,
That was it, I had it on.
atmosphere.
No, I just want to make the point that.
So the discussions they were having
There.
earlier too.
Yeah, okay, so look at this. So here's regular, give me a regular glass. This one, here's clear to
Clear.
me. Okay, so here, there's no heat reflected back, right? Basically, your heat is coming in. Here, and you can clarify what I mean by heat. Here, with the low E 366, it's not getting into the interior because the glass is reflecting it back out, which is what happens with, Jim can tell you a story about what happened with your glazing reflecting.
Well, I was gonna mention that. So we talked a little bit about the magnifying glass. Something that others have learned here is that if you make your insulating glass units negative, you now have a magnifying glass. I had to go to Massachusetts and do some inspection work on a job that had a fire.
You mean the glass was hourglass?
The glass is hourglass.
And what was causing that?
Well, that was the way it was made. The unit was assembled with a hot mount sealant, and it was assembled while it was still closed, sealed while it was still on. And so once it cooled off to room temperature, it was still in that negative position.
So if you have coatings that reflect radiant energy that concentrate rays by being a concave surface, because convex spreads it, so it's a glare problem. Concave focuses it, like London, that's where you get heating. So that's all I can really do with this irradiance meter demo. I mean, this demo was really about watching the radiometers.
So he was talking before this on the right here about vacuum insulated glazing. Jim was. You guys heard about that? So argon is the standard gas, krypton, xenon. But now they're putting spacers between the glass and actually doing vacuum.
Well, there's people conceptualizing that they can do that. It hasn't come out of the library yet. Conceptually, you can get R10 out of a double pane unit. But right now, nobody knows how to do that in custom sizes, in shapes, in tempered glass. It's something that works in cold weather. If you want an R10 window, don't you want it to work in cold weather?
Yeah.
Well, the one problem with this product is that it curls like a potato chip towards the cold side. The room side is expanding relative to that cold surface, and the entire glass panel curves in. So you got to design a window that can accommodate a quarter to a half inch movement on the edge.
So vacuum insulation isn't working.
It's a wonderful concept, but nobody's worked it out to scale at a price that you want to buy.
Right.
So what I want to show you is, so you remember my slide of 1,000 had 900 watts per meter squared in Port O'Connor? And so, if I go out there, it's probably like 600, 700 here. So here, on this now I've duplicated that reading with this distance. I want you to put your hand right where this meter is. It says 900. Feel what 1,000 watts per meter squared is. Now, so when you're out in the sun in Texas, this is the same amount of heat that your whole body is exposed to outside. It's insane, isn't it? I mean, when you're indoors and you start to get a tangible feeling for why that is, you're like out there. So what does this be to you? What's 1,000?
Sensitive on it.
250,
250?
round number.
Okay.
In
Now,
terms of BTU per square foot, yes.
okay, so now let's look at 10,000 foot candles. And I'll do a little, no zero should pop up here.
And so that one, the sensor's this.
Well, I'm going to go with 1,000 on this. So one way to test glass, which you can do, is just what I'm doing here. You space the meter and the source till you get a nice round, to a nice 100 number with zeros after it. Then, which you can do, that holds pretty well, right? Then you can take your glass and you can see what the transmittance is, because you know that it was 1,000. So it's just a quick way to get transmittance. And you can do the same with the irradiance meter. All right, so I wanted to just leave it. The last thing here was, a lot of this is combining glazing and shading, and this is where Zach is showing you some different fabrics. So this material, silver screen, is an excellent product for this on its own. You get view out, like you do with this, with a dark screen, and it has like a 4 to 5% transmittance. But this aluminum coating reflects heat back out. It has a very low solar heat coefficient. It couples with the glazing. So, but the only downside is that's what you see from the exterior. And some people may not like that. You know, another great, so a product that has just come out is this black fabric, which has a low emissivity thread in it. And so the downside of black fabric is you have low transmittance, but you have high solar heat coefficient because it absorbs heat. But this, because of its low emissivity thread, it acts like a white fabric on the outside. So you can, from the outside, you can see a dark fabric, and it's not as visually disturbing. So this is a great product, you know, as an alternative to the reflective material. You know, this is the typical Texas solar screen. This is a good quality solar screen, which goes on the outside, and this reduces heat by 50%. With, yeah, this was the percentage of openness they claimed. But you know, this just over a window. I'm glad you raised that up because we could.
It's been a while walking around after working with Matt. Everything. With the glare off of the car.
I mean, this helps you.
30 times.
You know, the problem with white is it interferes with the view, and these windows are good for this.
Oh my gosh, that one totally blocks it out. You can't see anything outside.
Well, you actually can. It's just that's the compromise. And
What's the center one?
the center one, that's white, and it's because it's white. It's interfering with your view on the inside. I just want to show you really good. This one. This is Mermet's aluminized material. Look at how nice that is for view, right? But so this is a great retrofit product when you have windows. It can just ruin the windows so if it can't handle the thermal load.
The interesting thing with the white is you seem to get a fair amount of a color shift as well.
Yeah, it's just color. So what I think this is heading towards is in order to fit the larger dynamic range to the comfort levels. We have automated systems where when it's hot, you might couple the shade with the glazing, and when it's colder, you can lift the shade up and get a little more heat coming in. And then when you have brightnesses outside that you can identify, you can bring the comfort shade where you need it. Right, so it's it's figuring out how to make it more adaptive.
So are these in?
Orientation. Each orientation is separately monitored, and with those typologies I showed you, you would figure out an operation to maintain visual comfort and daylight, and look at the energy balance. We're going to look at energy and thermal. We're going to look at thermal and visual at the same time and make a decision, like what is the best, right? Because you know if someone doesn't have enough light or it's uncomfortable, it defeats everything. They'd have to have daylight. So we're trying to maintain visual and thermal comfort and make the best decision. Some fabrics may perform better than others when we try to get all those parameters. All right, so that's really it. I wanted to.
What are those big pieces?
All right, the big piece is this. Well, this Jim can speak to. This is the Cardinal has top shelf coatings for.
What are the coatings made?
Well, this last one in particular is kind of the latest in the breed. This has actually got 2 low-E coatings in it.
Let's put them up there. I mean, explain, since we have these all.
You have one with a low-E coating on the inside face?
There's one in the space, and there's one facing the room.
Yeah, so you're actually touching the low-E coating.
Yeah.
But you can't feel it.
Now, the purpose of that is that it's decoupling you from the window there. This has got about an R5 for an insulating value, versus the standard one is about an R4. It's an incremental improvement. Takes that window to another level, but it takes that second.
Can you wash it?
Yeah. This is durable. This is the same basic coating you got on your phone. And then the other interesting perspective from the comfort side is that now that window is literally reflecting your body heat back at you.
Yeah.
You are warmer on a cold winter night standing in front of that window than you are next to the in front of the insulated wall. Because your body's in pretty good the heat supply.
So what I want to learn more about is coupling, how the fabric interacts with the coatings.
Well, it's gonna.
Because the fabric's going to reflect heat back to the coating on the window. Now, what does it happen? Say, if sun goes through and sun does it just keep getting reflected back?
Well,
So eventually
Like
some
the
will.
laser light comes out.
Okay, so let's say this is the exterior. This product is gonna have, 20-something% transmission. You put a shade in here, and what's the reflectivity of your shade?
For heat?
For solar.
SHGC.
Yeah, I don't know. Let's say let's say it's 20.
Your
Fine,
black
let's
one
just say
is like
25.
maybe 10%,
Okay, yeah.
something like that.
Zero.
So 20% comes in, 10% of that 20% reflects off, and then.
Does it get out?
And then, well, 20% of it will get out.
Right.
And so the impact that it's gonna have on the total solar heat gain will be very small.
Yeah.
But it's gonna be trapping that heat there.
Which is okay. I mean, once the heat gets in the building, it's in the building, but it's not over there where she is. It's better that it's.
Well, we were talking about systems that remove heat from the perimeter
Yeah.
before it gets in. We've coupled with some.
That'd be the best exterior shade.
Yeah.
Yeah, that's what I was saying. If you want, I mean, this is what I just want to integrate. Christopher II recap point was, he said, once the heat comes in, if it heats something up, I mean, once the sun comes in, why not putting those shades like outside? Then, and if you don't do that, like I'm not trying to general design, but if I want to see if it's going to be with like medium reflection, then we have less heat island effect overall on the bigger scale in the public space you walk. And then you have shade, or then you have the glass, then you have like integrated design probably.
Well, the most effective shade is always gonna be the exterior one.
Yes.
But of course, now then it's exposed to weather, and you have to operate it, and then you have to deal with those systems there. If you get a product like this that starts off at such a low solar gain to start with, now I look at those things as more modulating the visible. It isn't too much on the energy side.
Yeah.
It is more for taking care of the glare aspect.
When you need it down.
Yeah.
Because like you saw my skylights that I have in my studio, it wasn't until I started using this aluminized fabric that I got the heat under control when it's sunny, and then when it's not sunny. Without that material, it's perfect, just a amount of light. So you really need something, you have to modulate it constantly. So looking through, because I was saying the 2,500 candles per meter squared is about the limit. When you look outside now, that's about the highest level you see with this tent.
That's what I wanted to
But
explain here.
there's points when like the reflection off the windshield is gonna go higher on a white car, and that's when you really need something that brings down the transmittance.
Now, that's another generation of the low E coating where instead of allowing the maximum amount of daylight to come through, we've cut the VT down to 40%. So you've got some pretty good glare